Hello, welcome to lecture 5. In this lecture, we're going to finish up our chapter on Gauss's law by doing one last example. Then we'll get started on our chapter about electric potential and electric potential energy. For this last example, we're going back to our sphere of charge, but this problem is going to be a little bit more challenging because this time it's still insulating, it's still charged, but the charge is not constant. So the charge depends on where you are relative to the center. So if we think about our charge, it's not going to be very dense at the center, and it's going to be more dense as we get towards the surface. So maybe something like this. As always, my artistic skills leave a little bit to be desired, but hopefully this gives you the picture of what the charge density looks like. So not much charge in the center, lots of charge near the front. We want to find the electric field as a function of distance from the center. So we've done this problem already with uniform charge density. We're going to build on what we did then, but we're going to have to account for the fact that it's non-uniform. We'll begin by writing Gauss's law, so that's always the right place to start. Gauss's law says that the net electric flux through any closed surface is the integral of the electric field over the area of that surface, and that also is equal to the net charge enclosed by the Gaussian surface divided by our constant epsilon naught. So let's deal with the integral part first. We can go through this pretty quickly because we've done this already. So if we have a sphere of charge, the electric field lines will be radially outwards because of the spherical symmetry. So there's our electric field. I'm going to draw this sphere twice and my electric field lines twice. We always want to pick a Gaussian surface that reflects the symmetry of our charge. So our Gaussian surface is going to be a sphere. One of our Gaussian surfaces is going to have R less than R, and one of our Gaussian surfaces is going to have R greater than R. But they both look pretty similar. So when we do our integral of E dot dA, it's the integral over the surface of this sphere. In both cases, the little element of area points radially outwards. So whichever one we look at, area is radially out. And since electric field is radially out, the electric field and the area elements are parallel. So that gives us E times dA times cosine of 0, which is the integral of E times dA. As long as we're a constant distance away from the center, so on the surface of a sphere, the electric field is a constant. That comes out front of the integral. We've got the integral of E times the integral of dA, which is just E times the area of that sphere, which is E times 4 pi r squared. So for our left-hand side of Gauss's law, the integral of E dot dA, our net electric flux, is equal to E times 4 pi r squared. Okay, so that result is true whether we're inside the sphere or outside. Next, let's look at Q inside. So let's remind ourselves that Q in means the amount of charge inside the Gaussian surface. This time it's going to be a little bit complicated because our charge density is variable. So this one, for this example, is a bit complicated. Not impossible, just a little bit complicated. So let's think about how we're going to approach this. If we wanted to find the net charge inside our Gaussian surface, let's just draw ourselves a Gaussian surface that's inside of our sphere. So here's our Gaussian surface with radius r. The net charge is however much charge is inside this Gaussian surface. We can see that it's only part of the charge. So how do we find out how much? Well, we have to think about how would we figure this out? Well, I think if we broke this up into shells, so we took one little bit here, then we took a shell around that one, a shell around this one, and if we added up the amount of charge on every one of these shells, eventually we'd get the total amount of charge. Hopefully that makes sense. So we'll build up our sphere, our Gaussian sphere, by adding together a bunch of little charges. So what that means, if we're going to add up the charge on each shell, add up charge on each shell, what we're doing is an integral. So to add up the charge means we're adding up every little bit of charge on every shell, and what we'll get when we add up all those little bits of charge is the net charge inside. Okay, so dq means identify one of these little shells. So I'm just going to pick one and color it in. So why don't I pick this one and color it in? Because you always just have to identify one of your dq's. So this little bit of shell that I've colored in has a net amount of charge dq. How am I going to figure out the charge on that shell? Well, I'll use my same strategy as before. The amount of charge is equal to the density times the volume. The density has the symbol rho. Since it's a little bit of charge, it's going to have a little bit of volume. So I'm still using all of my same strategies. It's just eventually I'm going to stick in something here for my rho. So my dV, why don't we just write down what we mean by dV? dV equals volume of one little shell. How do we write down the volume of a shell? Well, for the volume of a shell, what we can do is we can take the area of the shell and multiply it by the thickness. Area times thickness gives us volume. So equals area times thickness. We do know how to find an area. That's just going to be 4 pi r squared, and the thickness is just going to be how thick it is. Okay, so let's get some notation here. We've already used r for the radius of our Gaussian surface. We need a different r to be the radius of our shell. So I'm going to call that r primed. So from the center to my shell is going to be a distance of r primed. So my shell has radius r primed, and the thickness is a little bit in that direction. So the thickness, from here to here is the thickness. That's a little bit of r primed, so dr primed. So my shell has radius r primed, thickness dr primed, because it's a little bit in that area direction. So for my area times thickness, I'm going to get 4 pi times r primed squared times dr primed. Okay, I think we're pretty close to good to go. I want to integrate dq, add up all these little bits of charge to give me my total charge. dq stands for a charge on one of these shells. To find that charge, we'll do density times the volume of the shell. The volume is the area times the thickness. So the area is the area of a shell, 4 pi r squared, and the thickness is a little bit in the r direction. And we're just using r primed here instead of r, because r is already taken to be the radius of our Gaussian surface. Let's get going now on finding the net charge inside our Gaussian surface. The net charge, Q in, is going to be the integral, or the sum, of each little bit of charge on each individual shell. We said that each little bit of charge was equal to the density times the volume of each little shell. Our density rho is a constant alpha times the radial position, and the radial position of our little shell we called r primed. dV means the volume of each little shell. The volume is going to be the area, 4 pi r primed squared, times the thickness, dr primed. Okay, now we can take our constants out in front of the integral. Alpha times 4 times pi outside of the integral of r primed cubed. That comes from r primed times r primed squared times the thickness dr primed. Okay, this is an integral we know how to evaluate, but first we should put our limits on. So we want to add up all the charges on all the little shells. So we'll start at the beginning where r primed equals 0, and we'll stop when we get to the surface of our Gaussian sphere where r primed equals r, 0 to r.
So this is equal to alpha times 4 times pi. The integral of r primed cubed is r prime to the power of 4 divided by 4. That's going to be evaluated at our limits. We see that we've got a 4 on top and a 4 on bottom, so we can divide through by 4. And that gives us alpha times pi. Put in our limits, so we've got r to the 4, subtract 0 to the 4, leaves us with our net result that the net charge enclosed by our Gaussian surface is alpha times pi times r to the 4. Okay, that was some work. Hopefully you were able to follow it all through. Now we've already figured out the integral side, and now we've just figured out Q in. We can go ahead and put those together to find the electric field. So to put it all together, we'll use Gauss's law. The integral of E dot dA is Q in over epsilon naught. We're going to begin with finding the electric field inside our insulated sphere. The integral of E dot dA is equal to E times 4 pi r squared, where r is the radius of our Gaussian surface. And this result comes from the spherical symmetry of the problem. We added up the charge on a bunch of little shells to find that Q inside was equal to alpha times pi times r to the 4, where r is the radius of our Gaussian surface. Okay, putting these together now, the integral of E dot dA, E times 4 pi r squared, is equal to Q inside, alpha times pi times r to the 4, divided by epsilon naught. Can simplify a little bit. We have a pi on both sides, so we divide through by pi and they cancel. We've got r squared on this side, so we divide both sides by r squared to leave us with r squared on the right-hand side. Now let's solve for E. E, if r is less than the radius of the sphere, is equal to alpha times r squared divided by 4 times epsilon naught. Because electric field is a vector, the direction is outward, radially outward. Okay, that's our electric field inside. What about outside? For finding our electric field outside the sphere, we'll still pick a Gaussian surface which is a sphere with radius r, but this time this radius has to be bigger than the entire insulator because we want to be outside. So here's our radius r. To find the net charge inside, we have to look at what charged object is inside the Gaussian surface. Well, the charged object inside the Gaussian surface is just the insulating sphere. So our Q inside equals the charge on the insulating sphere. Okay, so it's the whole charge on the sphere because that's the only thing with charge on the insulator. Okay, we're going to find that exactly the same as we did before. Q in is going to be the sum of all the little bits of charge. We'll break our sphere into shells again. So a bunch of little shells throughout the whole thing. And we're going to have to add up the charge on every single shell. So we'll do it the same way. We'll identify one little bit of shell. We'll shade that in. That little bit of shell has charge dq. It has radius that we'll call r primed. And it has thickness that we'll call dr primed. So we're following exactly the same steps. The radius of our sphere is capital R. So when we want to find the integral of dq, we're doing the integral of the density times the volume. The density is our constant alpha times the radial position r primed. The volume is the area, 4 pi times r primed squared times the thickness dr primed. Take our constants out front, we get alpha times 4 times pi times the integral of r primed cubed dr primed. This time the limits of our integral are from the center of the sphere because we have to start at the inside at the beginning. And where we'll stop is when we hit the surface of the sphere because that's the last place where we have charge. So we go over the entire charged object. So that's going to be alpha times 4 times pi times r primed to the power of 4 divided by 4, evaluated at r and 0. Our 4's divide out and we are left with our Q inside equals alpha times pi times the radius of the sphere to the power of 4. Okay, now we'll put these things together with Gauss's law. The integral of E dot dA is E times 4 pi r squared. The Q inside is alpha times pi times r to the 4. got to divide our Q inside by epsilon naught. We've got a pi on each side, so we'll solve for our E value. E is equal to alpha times r to the 4 divided by 4 times epsilon naught times r squared. Electric field is, of course, a vector, and the direction is going to be radially outwards. So there's our electric field outside the sphere. The problem doesn't ask us to, but we could, of course, graph this. To plot our electric field, let's put in a set of axes. I'll draw it right under the sphere. So we'll put r on the horizontal, we'll put electric field on the vertical. We know that if r is less than r, if we're inside the sphere, our electric field is alpha times r squared times 4 divided by 4 times epsilon naught. So this increases as r squared until we hit the radius. So it goes up something like this. Electric field proportional to r squared. When we're at the radius, if r equals r, then our electric field, what we can do is we can just plug r in here. So little r equals big R. Or in this equation, we can plug in little r equals big R. And what we get is the same in both cases. E is equal to alpha times r squared over 4 epsilon naught. That's going to be our maximum value of electric field. And then once we're outside, this is where our distance is outside the sphere, our electric field falls off as 1 over r squared. So E goes as 1 over r squared when we're outside. So that's what the plot of electric field as a function of position would look like.